Following from the introduction to vectors, in this video we're going to go through applications of vectors and mainly through geometrical shapes. In the previous video there were a few examples where some lines were drawn just to show how you can geometrically visualize vectors. In this question I'm going to go through a long example, and the example builds up on how you can prove or explain all these vectors using given letters. Just a tiny edit that this question is A. So we have this geometrical shape and we have all of these points labeled with capital letters, but we have two main vectors defined. So we have A and then we have B. And in the question, they will tell you what A and B are. So A is the vector from O to A. So if I go from O to A, this is my vector A, and O to B will be the vector B. And notice how vectors are in bold. AQ is half of A. This is where it didn't make sense to have half of B, because B is on a horizontal direction and AQ is on a slanted direction. But don't take the diagrams accurately. Just stick with what the question is shown. This question is taken from a new book, hence some mistakes would be found. And then we have BR is equal to B as well. So notice how this looks smaller than OB, but again, don't worry about the scale. This is B as well, and this is half of A. So it's good to label your diagram. And then we have AP is 2 of BA. So if I have BA, then AP would be double that BA. So let's just write it there, BA. So the first example is a nice one to show you, part A is a nice example to show you how you can describe different line segments using vectors. So if I'm going to start with A, and I want to express BA in terms of A and B, it means I want to move from B to A using only the vectors A and B. So if I want to move from B to A, it's ideal to move in this direction, just upwards. But there is no vector that would take me from B to A straight away on this line. We use the given vectors, which is, well, let me go backwards on B and then forward on A. So this backward on B is a negative B, and then I go in the A direction, so plus A. And this is the best way to describe how you can move from B to A using the given vectors. Now, you could also go a positive A and then a negative B, and that would still take you to the same position. So it doesn't have to be in that particular order. It could be A minus B. So this is just something to point out, but keep in mind the signs. And then B to P. So moving from B to P, well, I have to move B to A and then A to P. Well, we have B to A. Let's just write that. I need to move B to A and then A to P. We have B to A from the first part. It's negative B plus A. And AP, well, we have a way to describe AP, and that's 2B of A. And we have B of A. So this is 2B of A. And we have B of A, which is negative B plus A. Now, you don't have to go through these really tiny steps every single time. I just want to show you how it looks like. So B to A and then A to P, and then you can just solve it like you would do with any algebraic problem. So I have negative B plus A, and then you expand out the bracket. So all the algebraic rules apply, because this is like scalar multiplication on these vectors. Negative negative 2b plus 2a, and then just solving them, I get negative 3b plus 3a, and similarly you can write 3a minus 3b. So this would work as well. So this was for part A, quite straightforward on how you could solve this problem. If we go into part B, we want to express RQ in terms of A and B as well. So I will use the same process as breaking it down into different parts. So let me just go on a different slide. So RQ is basically going from R to Q. Let's use the available positions that we have. So I could go R to B, B to A to Q. That's a possible direction. I could go R to O and then O to Q as well. That's another possible direction. Let's try R to B, B to A, and then A to Q. R to B is basically the opposite of B to R. So it's the negative of B to R. And then we have B to A and then A to Q. Now you can try going R to B, B to O, O to A to Q as well, and I would encourage you to try it just to check that you get the right answer. Negative B to R would just be negative B, because BR is just B here. BA would be what we found in the previous part, which is negative B plus A. So I have negative B plus A. And then AQ is just half of A, so I just add half of A. And notice how I'm taking care of the directions that I'm going in. So I've recognized that RB is the opposite of BR, so I have to put a negative. So you need to be aware of these parts. We just expand out. I get a negative B plus A plus a half A. And just simplify it as you would. So this is negative B plus 3 over 2A. And that's a final answer on part B. So for part C, we have two vectors again that we need to describe. So we have QA and QP. Let's try QA first. So QA should be quite easy to do. QA is basically the opposite of AQ. And we know that AQ is half of A, which means QA will be just negative half of A. So quite straightforward. So using this, it will be useful to find QP. So Q to P, obviously there's no line here, but in order to get from Q to P, I'll just go the opposite of, I'll go Q to A and then A to P. So I'll go Q to A and then A to P. So again, remember, you're breaking it down into parts that you know. Q to A we found already, which is negative half of A. Even if you didn't find it, it would be easy to see that it's the opposite of A to Q. And then A to P is 2B of A. And we already have B of A from a few slides. So it's 2, and then looking back at part A, B to A is negative B plus A. So we have, over here, we have negative B plus A. And again, expanding out and simplifying, so we get negative 2B plus 2A, and this would simplify to negative 2B plus 3 over 2A. And looking at the last question, we have, so using the vectors for RQ and QP, I need to show that RQ and P lie on a straight line. So RQ and P lie on a straight line. Usually they would draw a line here, so connecting P to Q to R. And sometimes it might seem so from the diagram, sometimes it wouldn't show, but remember you need to use vectors to prove that they are. So here's a fact that you should know about vectors. That if you have an x, y, and z is a line, then x to y as a vector should be a scalar multiple of y to z. So these two should share a point. In this case it's y, so x, y, and y, z, they share the point y, and they should be scalar multiples of each other. So if I have the line r, so let's erase this. If I have the line RQP, I want to see what RQ is and what QP is, which is what the question asks you to use. RQ we found in part B, and QP we found in part C. Now notice they share the same point, and let's just use the values we got. So we have for QP we have negative 2b plus 3 over 2a, and for RQ we have the same thing, negative 2b plus 3 over 2a. So usually either you're going to get a scalar multiple, so maybe this is QP would be double RQ, but in this case we got the same value, so we'd say that you have equal vectors and they share a common point. So this is an important factor, which is Q. Therefore, they're on a straight line, or you can say RQP forms a straight line. So this is an interesting fact to know about when you're dealing with vector geometry. Another video will come up real quick just discussing how to use vector questions that involve ratios. It shouldn't be too hard. It just explains how to apply them. As soon as you can translate those, it would be easy to do, just like this video.